What is not cannot be. That's what the philosopher Parmenides claimed 2,500 years ago. When we try to think of nothing, our mind already turns it into something. Naming nothing makes it an idea, and ideas exist. But if nothing cannot be, then why must something exist? Why are we trapped inside existence at all? This might be the oldest and strangest question humans have ever asked. In the summer of 1714, in a quiet study overlooking the gardens of Hanover, Gottfried Wilhelm Leibniz posed a question that would haunt philosophy for centuries. Pourquoi a-t-il quelque chose plutôt que rien? That is, why is there something rather than nothing? This wasn't merely academic curiosity. It was intellectual lightning striking the deepest foundations of existence itself. Leibniz understood that everything around us, every breath we take, every star burning in the cosmic void, represents a profound deviation from what logic suggests should be the natural state, absolute emptiness. But here's where Leibniz's genius becomes apparent. He didn't stop at asking the question. He demanded an answer that could bear the full weight of reality itself. Leibniz operated on a philosophical principle that remains revolutionary. Everything that exists must have a sufficient reason for its existence. Nothing happens without cause. No truth exists without explanation. This principle led him inexorably to a startling conclusion. If we trace back the chain of explanations, why this exists because of that, why that exists because of something else, we cannot continue infinitely. The chain must terminate somewhere, but where? Here, Leibniz made his boldest move. He declared, "The sufficient reason is found in a substance which is a necessary being, bearing the reason for its existence within itself." What did he mean by this cryptic formulation? He meant that at the foundation of all reality must exist something that doesn't depend on anything else for its existence, something that exists by the very nature of what it is. Think of it this way. Contingent things, like planets, people, particles, exist because other things brought them into being. But a necessary being exists because non-existence would contradict its essential nature. Just as a triangle must have three sides by definition, this being must exist by definition. Leibniz's answer wasn't merely theological, it was logically inevitable given his premises. If everything requires sufficient reason, and infinite regress is impossible, then something must exist that carries within itself the complete explanation for its own existence, and by extension the existence of everything else. This necessary being doesn't exist because something made it exist. It exists because its non-existence would be a logical contradiction, like a married bachelor or a square circle. But here's what makes Leibniz's solution both brilliant and troubling. If we accept that reality requires a necessary foundation, we must ask why this particular necessary being rather than some other. Why should the foundation of existence possess consciousness, will, and creative power, rather than being merely mathematical or structural? Leibniz believed he had solved the deepest mystery of existence. Whether his solution merely relocated that mystery to an even deeper level remains one of philosophy's most contested questions. The man who gave us calculus and binary mathematics left us with perhaps the most beautiful and haunting question ever formulated, and an answer that continues to challenge every assumption we hold about the nature of reality itself. What strikes you most about Leibniz's approach, the elegance of the question itself, or the audacity of his proposed solution? Now let's start today's documentary, Why Does Anything Exist? Silence. Complete, absolute silence. Yet here you are, listening to these words. Your neurons fire, your consciousness processes meaning, your very existence contradicts the void. This singular fact that anything exists at all represents the most profound puzzle confronting human intellect. Consider the mathematical probability of nothingness. Zero requires no explanation, no cause, no origin. It simply is, or rather, isn't. Zero is elegant, complete, self-evident. Yet we inhabit a universe of staggering complexity. 10 to the power of 80 atoms arranged in patterns so intricate they generate consciousness capable of contemplating their own existence. Why didn't reality choose the simpler path? This question has haunted humanity's greatest minds across millennia. 2,500 years ago, in ancient Greece, Parmenides wrestled with the fundamental nature of being and non-being. He recognized something crucial. What is not cannot be thought or spoken of meaningfully. If absolute nothingness were truly possible, we could never conceive it, never reference it, never use it as a comparison point for existence itself. The question lay dormant for centuries until Gottfried Wilhelm Leibniz, the brilliant German polymath, articulated it with crystalline precision in his 1714 work, Principles of Nature and Grace. Why is there something rather than nothing? Leibniz understood this wasn't merely philosophical speculation. It demanded a sufficient reason, a logical foundation for reality's very presence. Ludwig Wittgenstein, that titan of 20th century philosophy, declared the mystical core of existence lies not in how the world is, but that it is. Meanwhile, Martin Heidegger elevated this inquiry to supreme importance, calling it the fundamental question of metaphysics, the gateway through which all other philosophical investigations must pass. But here's what makes this question truly extraordinary. It isn't confined to academic halls or theological seminaries. Every conscious being, upon first grasping their own existence, encounters this puzzle. Children ask it spontaneously. Scientists confront it when their equations trace back to initial conditions. Artists express it through their desperate attempts to capture meaning from apparent chaos. Yet we face an immediate logical obstacle. How can we meaningfully discuss absolute nothingness? Every attempt to describe it requires language, concepts, minds, all of which presuppose existence. The very act of questioning nothingness proves something exists to do the questioning. Philosophers have long recognized this paradox. No empirical test could ever confirm the hypothesis there is absolutely nothing, because the testing itself requires an observer, instruments, space, time, the entire apparatus of existence. We cannot experience non-existence. We cannot observe the absence of observation itself. This creates a peculiar epistemological situation. We're attempting to understand reality by comparing it to something we can neither know nor encounter. Consider the implications carefully. If pure nothingness is not just practically but logically inconceivable, then perhaps our question contains a hidden assumption. We're asking why something exists as if nothing were a genuine alternative. But what if absolute nothingness isn't actually possible? What if existence in some form is inevitable? This realization transforms our inquiry. Instead of asking why reality chose existence over non-existence, we might ask, what kind of existence was inevitable? And why does it manifest in precisely this form? The question shifts from wondering why there's something rather than nothing to understanding why there's this particular something with these specific laws, these exact constants. This precise configuration of matter and energy that allows for galaxies, stars, planets, and ultimately conscious observers capable of asking such questions. Throughout history, attempts to answer this fundamental question have revealed the deepest assumptions underlying human thought. Some propose that existence is a brute fact requiring no further explanation. Reality simply is, and demanding reasons represents a category error. Others argue that only a necessary being, something that cannot not exist, provides sufficient grounding for contingent reality. Each approach reveals something crucial about the nature of explanation itself. When we ask why, what kind of answer could possibly satisfy us? A cause implies something prior, but then we can ask about that prior cause. A logical necessity implies a framework of logic, but we can ask why that particular logical framework exists. A mathematical foundation assumes the reality of mathematical objects and relationships, but we can inquire about their ontological status. These recursive explanatory chains suggest something profound about consciousness itself. We are beings constituted by the very existence we're trying to explain, using minds that are products of the reality we're attempting to understand. We're not external observers studying existence from outside, we're existence studying itself from within. This reflexive character of the question provides our first crucial insight. The fact that the universe has evolved conscious beings capable of wondering about their own existence is itself part of the phenomenon requiring explanation. Existence isn't merely a collection of particles and forces. It's a reality complex enough to generate observers who can contemplate the mystery of their own being. As we stand at the threshold of this investigation, we face a choice. We can treat this as an abstract intellectual puzzle, or we can recognize that we ourselves are living embodiments of the very mystery we seek to understand. Every breath you take, every thought you think, every moment of consciousness represents the universe's ongoing answer to the question of why anything exists at all. The question that began as philosophical speculation becomes intensely personal. You're not merely asking why there is something rather than nothing. You are something asking about its own inexplicable presence in a reality that, by all logical rights, should never have existed at all. The universe began 13.8 billion years ago in an event we call the Big Bang. Yet this fundamental statement immediately confronts us with a profound puzzle. What preceded this cosmic genesis? Was there truly nothing before space and time themselves came into existence? Traditional thinking suggests that from absolute emptiness, complete non-existence, our cosmos somehow materialized. This notion violates our most basic intuitions about causality. How can something emerge from literally nothing? The answer lies in a revolutionary understanding that has transformed our comprehension of reality itself. The Big Bang represents not merely an explosion in space, but the emergence of space itself. Within the first fraction of a second, the universe expanded from a state of infinite density and temperature to a region large enough to contain the seeds of every galaxy we observe today. This initial singularity marks the boundary of our ability to trace cosmic history backward through conventional physics. Yet this beginning immediately raises fundamental questions. If we accept that the universe had a definitive starting point, we must confront what philosophers call the principle of sufficient reason. Everything that exists must have an explanation for its existence. What could possibly explain the emergence of space-time from a state of absolute non-being? The conventional response suggests divine intervention or supernatural causation. However, advances in theoretical physics have provided a radically different framework for understanding cosmic origins, one that operates entirely within natural law. Quantum mechanics has fundamentally altered our conception of nothingness. What we previously understood as empty space, the vacuum, is revealed through quantum field theory to be a dynamic, energetic medium teeming with activity. This quantum vacuum represents the lowest possible energy state, yet even this minimum contains fluctuations that can spontaneously generate particles and antiparticles. Lawrence Krauss's groundbreaking work demonstrates that these quantum processes can account for the universe's emergence without invoking supernatural causes. The quantum vacuum, far from being inert emptiness, contains sufficient energy and inherent instability to spawn entire cosmic structures. Virtual particles continuously appear and disappear within time frames permitted by Heisenberg's uncertainty principle. creating a foundation from which reality can crystallize. The mathematics supporting this framework are precise and testable. Quantum field equations predict that vacuum fluctuations will inevitably produce matter-energy pairs. When these fluctuations occur on cosmic scales, they can generate the initial conditions necessary for Big Bang cosmology. The universe emerges not as a violation of physical law, but as its inevitable consequence. The transition from quantum vacuum to expanding universe follows well-established physical principles. Inflation theory, supported by cosmic microwave background observations, describes how quantum fluctuations in the early universe's scalar field could drive exponential expansion. These same fluctuations provide the density variations that eventually collapsed under gravity to form galaxies and stars. Stephen Hawking's calculations show that space-time itself can emerge from quantum processes. In his formulation, imaginary time eliminates the need for a boundary condition at the universe's beginning. The cosmos becomes self-contained, requiring no external cause for its existence. This represents a complete inversion of traditional causality arguments. Recent calculations by Alexander Vilenkin and others demonstrate that false vacuum states are inherently unstable. Through quantum tunneling, these states will inevitably decay into true vacuum bubbles, expanding regions of space-time that could constitute entire universes. Our cosmos may represent just such a vacuum decay event, emerging spontaneously from pre-existing quantum fields. The critical insight is that nothing, properly understood through quantum mechanics, is not the absence of everything, but rather the simplest possible something. The quantum vacuum contains fields, energy, and the laws of physics themselves. It represents a baseline reality from which complexity can emerge through purely natural processes. This reframing eliminates the philosophical problem of creation ex nihilo. We are not asking how something can arise from absolute nothingness, but rather how complex structures develop from simpler quantum foundations. The answer involves well-understood physical mechanisms, symmetry breaking, phase transitions, and gravitational collapse. Yet this scientific triumph introduces new mysteries. If quantum fields and their governing laws provide the foundation for cosmic emergence, we must ask, why do these particular laws exist? What determines the specific parameters that allow universes to form? The quantum vacuum may explain our cosmos, but it presupposes a deeper structure of mathematical relationships and physical principles. The question of existence has not been eliminated, merely transformed. Instead of asking why anything exists rather than nothing, we now ask why the quantum vacuum, with its specific properties and governing equations, exists rather than some alternative configuration. The mystery deepens rather than resolves. This shift in perspective reveals that the boundary between something and nothing may be fundamentally misdrawn. What we call nothing, the quantum vacuum, contains the seeds of everything. True nothingness, a state completely devoid of fields, laws, and possibilities, may be not just unlikely but logically incoherent. If so, the existence of something becomes not miraculous but inevitable. Absolute nothingness presents an extraordinary logical puzzle that has confounded philosophers for millennia. When we attempt to conceptualize complete emptiness, the total absence of everything, we encounter an immediate contradiction. The very act of thinking about nothingness requires a thinking mind, which by definition constitutes something. This creates what philosophers call the observational paradox. No conscious entity could ever witness true nothingness, because the presence of an observer automatically negates the condition being observed. Consider the implications. If we emptied the universe of all matter, all energy, all fields and all structures, what would remain? The ancient Greek philosopher Parmenides recognized this conundrum 25 centuries ago, arguing that what is not cannot be thought or spoken of coherently. His reasoning was deceptively simple, yet profound. To think of nothing, you must think of something, even if that something is the concept of absence itself. Modern neuroscience reveals why our minds struggle with this concept. The human brain evolved to process information about existing objects, relationships, and patterns. When we attempt to visualize nothingness, our neural networks inevitably fill the void with darkness, space, or potential, all of which are decidedly something rather than nothing. Contemporary physics has fundamentally transformed our understanding of what we once considered empty space. The quantum vacuum, what physicists now recognize as the lowest possible energy state, is far from the inert void our intuitions might suggest. Instead, it seethes with activity at the subatomic level. Quantum field theory demonstrates that even in perfect vacuum conditions, virtual particles continuously materialize and annihilate in fleeting moments. These quantum fluctuations are not merely theoretical constructs, they produce measurable effects. The Casimir effect, first predicted by Dutch physicist Hendrik Casimir in 1948 and subsequently verified experimentally, shows that two uncharged metallic plates in a vacuum will attract each other due to quantum fluctuations in the electromagnetic field between them. This revelation carries profound implications. If the most empty state physics can describe still contains energy and activity, then true nothingness may be not merely difficult to achieve, but fundamentally impossible. Nobel laureate Frank Wilczek captured this insight succinctly when he observed that nothing is unstable. The quantum vacuum appears to be inherently restless, constantly generating something from what we previously considered nothing. The scientific redefinition of nothingness forces us to reconsider our entire framework for understanding existence. When physicists like Lawrence Krauss argue that something can arise from nothing, they are referring to this quantum vacuum state, not to absolute philosophical nothingness. This distinction is crucial because it shifts the entire foundation of our inquiry. In quantum mechanics, the vacuum is better understood as a field in its ground state rather than as empty space. Quantum fields permeate all of reality, and even at their lowest energy levels, they retain zero-point energy, a residual quantum mechanical motion that persists even at absolute zero temperature. This zero-point energy is not merely academic. It has real, observable consequences in the behavior of matter and light. The implications extend beyond particle physics into cosmology itself. Modern theories suggest that quantum fluctuations in the early universe's vacuum state may have seeded the density variations that eventually grew into galaxies and cosmic structures. In this framework, the large-scale architecture of the universe traces its origins to quantum uncertainties in what we might naively consider empty space. If true nothingness is unstable or even impossible, we confront what philosophers call the persistence problem. Why should any particular state of existence maintain itself over time? If nothingness cannot persist because it is inherently unstable, then perhaps existence is the only stable configuration reality can assume. This perspective suggests that the question, why is there something rather than nothing, may be based on a false premise. The question assumes that nothingness is a viable alternative to existence, but if nothingness is fundamentally unstable or incoherent, then existence becomes not just probable but inevitable. Theoretical physicist Stephen Hawking explored this concept in his work on quantum cosmology, suggesting that the universe could emerge spontaneously from quantum tunneling events in a primordial vacuum state. In this model, the Big Bang represents not the creation of something from nothing, but rather a phased transition from one type of quantum state to another. The redefinition of nothingness creates a new form of the original question. If what we call nothing actually contains quantum fields, energy fluctuations, and physical laws, then where do these underlying structures originate? We have not eliminated the mystery of existence, but merely pushed it one layer deeper into the foundations of reality. This recursive nature of the question suggests that we may be approaching the limits of reductive explanation. Each answer we discover seems to require its own explanation, creating an infinite regress of why questions. The quantum vacuum explains how universes might emerge spontaneously, but the existence of quantum mechanics itself remains unexplained. Some philosophers argue that this regress is not a failure of explanation, but rather a feature of how explanation necessarily works. Perhaps the deepest questions about existence cannot be answered by finding prior causes, but only by recognizing the logical structure of reality itself. In this view, the laws of quantum mechanics are not contingent facts that require explanation but necessary features of any coherent reality. The impossibility of observing true nothingness reveals a fundamental boundary in human knowledge. We can theorize about absolute emptiness, construct mathematical models of void states, and explore the logical implications of non-existence, but we cannot directly access or verify these concepts through empirical observation. This limitation is not merely practical, but appears to be inherent in the nature of observation itself. Any measurement or detection requires some form of interaction, and interaction presupposes the existence of both observer and observed. The very tools we use to investigate reality, consciousness, instruments, mathematical frameworks, are themselves forms of something rather than nothing. This observational boundary suggests that the question of existence may be as much about the nature of knowledge and consciousness as about the nature of reality itself. The fact that questioning minds exist to ask, why is there something rather than nothing, may be integral to any complete answer to that question. The mystery of nothingness thus reveals itself as more than a simple absence to be explained. It represents a fundamental limit to reductive explanation and a gateway to deeper questions about the nature of existence, consciousness, and the logical structure of reality itself. Whether this boundary represents an insurmountable obstacle or a clue to reality's deepest nature remains one of philosophy's most compelling open questions. The vacuum of space appears deceptively empty, yet beneath this apparent nothingness lies one of the most extraordinary discoveries in modern physics, a discovery that fundamentally challenges our understanding of existence itself. When physicists speak of vacuum, they do not refer to the absence of everything. Instead, quantum field theory reveals that the vacuum state represents the lowest possible energy configuration of all quantum fields permeating space. This ground state remains far from inert. Virtual particle pairs continuously materialize and vanish within time frames so brief they escape direct detection. Yet their effects prove measurable through phenomena such as the Casimir effect and vacuum polarization. Consider the implications. Even in the most perfect vacuum achievable, where every atom has been removed and electromagnetic radiation eliminated, the quantum fields themselves persist. These fields fluctuate according to Heisenberg's uncertainty principle, which dictates that energy and time cannot be simultaneously determined with absolute precision. Consequently, quantum mechanics permits, indeed requires, temporary violations of energy conservation, allowing particle pairs to borrow energy from the vacuum and exist briefly before annihilating back into nothingness. The mathematics underlying these vacuum fluctuations emerges from quantum field theory's foundational equations. The vacuum expectation value of the energy density, while finite after appropriate renormalization procedures, demonstrates that empty space possesses structure and dynamics. This revelation transforms our conception of nothingness from passive void to active medium. Building upon these vacuum properties, contemporary cosmology proposes that our entire universe may represent a quantum fluctuation scaled to cosmic proportions. This hypothesis, advanced by physicists including Stephen Hawking and Alexander Vilenkin, suggests that the Big Bang itself constitutes a quantum tunneling event from a false vacuum state. The mechanism operates through vacuum decay, where a metastable false vacuum spontaneously transitions to a lower energy true vacuum state. During this transition, enormous amounts of energy release, potentially generating the initial conditions observed in cosmic microwave background radiation. The mathematics describing this process draws from semi-classical approximations to quantum gravity, where the probability of vacuum decay depends exponentially on the action of instantaneous solutions to the Euclidean field equations. Hawking's no-boundary proposal provides a particularly elegant framework for understanding cosmic origins. By applying quantum mechanics to the universe's wave function itself, this approach eliminates the need for initial conditions entirely. The universe emerges from quantum superposition, with the path integral over all possible geometries, determining the probability amplitude for different cosmic configurations. Recent calculations by physicists such as Sean Carroll and Jennifer Chen demonstrate that vacuum fluctuations in de Sitter space can indeed produce pocket universes with properties resembling our own. Their models show how inflation naturally arises from quantum field dynamics in curved space-time, providing both the mechanism for cosmic expansion and the seed fluctuations that eventually form galaxies and stars. Yet this quantum explanation for cosmic origins reveals a profound limitation. While quantum mechanics may explain how something emerges from apparent nothingness, it presupposes the existence of quantum mechanical laws themselves. The Schrödinger equation, uncertainty principle, and field theory commutation relations all represent mathematical structures that must exist prior to any quantum creation event. This observation shifts the fundamental question from why is there something rather than nothing to why do these particular laws govern reality. The vacuum fluctuation mechanism requires specific values for fundamental constants, the fine structure constant, Planck's constant, the speed of light, whose existence remains unexplained by the theory itself. Furthermore, the mathematical framework underlying quantum field theory assumes the existence of Hilbert spaces, operator algebras, and complex number systems. These abstract mathematical structures appear to possess a reality independent of physical phenomena, yet their necessity for describing quantum creation raises questions about their own origins. The concept of quantum vacuum thus reveals itself as a sophisticated form of something rather than genuine nothingness. It contains fields, energies, symmetries, and dynamical laws, an entire mathematical architecture that enables creation. This recognition forces us to acknowledge that quantum mechanics has redefined, rather than eliminated, the mystery of existence. The quantum mechanical approach to cosmic origins carries profound implications for our understanding of reality's fundamental nature. If the universe emerges from quantum processes, then the probabilistic character of quantum mechanics suggests that existence itself possesses an irreducibly statistical character. Multiple universe scenarios naturally follow from this perspective. Eternal inflation models, developed by Alan Guth and Andre Linde, predict that vacuum decay events continuously generate new pocket universes with varying physical properties. In such scenarios, our universe represents just one realization among infinite possibilities, with its particular properties determined by quantum mechanical probability distributions. The anthropic principle then provides a selection mechanism. We observe a universe compatible with our existence precisely because incompatible universes contain no observers to question their properties. This reasoning suggests that the apparent fine-tuning of physical constants reflects observational bias rather than design. However, this multiverse explanation merely relocates the mystery to a higher level. Why should the metaversal laws governing eternal inflation exist? What determines the probability distributions for vacuum decay? The quantum mechanical framework, while providing mechanisms for creation, ultimately rests upon mathematical foundations whose existence it cannot explain. The quantum approach to cosmic origins thus illuminates both the power and limitations of scientific explanation. It demonstrates how sophisticated physical theories can account for the universe's emergence from apparent nothingness, yet simultaneously reveals how such explanations necessarily assume the prior existence of mathematical structures and physical laws. The question of existence, rather than being answered, transforms into deeper questions about the nature of mathematical reality and the origins of natural law itself. This transformation represents not failure but progress, a refinement of humanity's most fundamental question into forms amenable to continued investigation. The quantum vacuum, while not the ultimate answer to why anything exists, provides crucial insights into how existence propagates and evolves once the proper conditions manifest. Mathematics governs every particle interaction, every stellar formation, every quantum fluctuation in our universe. Yet this raises a profound question that strikes at the heart of existence itself. Do mathematical truths exist independently of physical reality, or do they emerge from it? Consider the number 2. Before humans evolved, before Earth formed, before our sun ignited, did the concept of two-ness already exist somewhere in the fabric of reality? When we discover that 2 hydrogen atoms combine with 1 oxygen atom to form water, are we uncovering a truth that was always there, waiting to be found? This distinction between discovery and invention represents one of the most consequential debates in the philosophy of mathematics. If mathematical structures are discovered rather than invented, then we confront a startling possibility. Mathematics might constitute the fundamental architecture of existence itself. Bertrand Russell and Alfred North Whitehead, in their monumental work Principia Mathematica, argued that mathematical truths possess a necessity that transcends our physical universe. These truths, they contended, must hold in all possible worlds. The theorem that the square root of 2 is irrational remains valid whether our universe exists or not. The geometric relationships within triangles persist regardless of whether space and time emerged from the Big Bang. This mathematical realism suggests that numbers, geometric forms, and logical relationships inhabit an eternal realm, what Plato termed the world of forms. In this view, when mathematicians prove theorems, they are not creating new knowledge, but rather mapping territories in a landscape that exists independently of human minds. But notice the radical implication. If mathematical structures necessarily exist, then perhaps physical reality itself emerges as a consequence of mathematical necessity. The universe might not be a collection of things that happen to follow mathematical laws, but rather the inevitable manifestation of mathematical relationships themselves. How does this transition occur? How do abstract mathematical entities give rise to concrete stars, planets, and living beings? Physicist-philosopher Dean Rickles proposes that numbers and their relationships could serve as the fundamental substrate from which physical phenomena emerge. In this framework, particles are not things that have mathematical properties, they are mathematical structures. String theory provides a compelling example of this principle in action. According to string theorists, the fundamental constituents of matter are not point particles, but rather vibrating mathematical objects, strings existing in multiple dimensions. The different vibrational modes of these strings correspond to different particles. In essence, an electron is not something that obeys mathematical equations. An electron is a mathematical equation made manifest. This perspective transforms our understanding of physical laws. Newton's law of universal gravitation, Einstein's field equations, Schrödinger's wave equation, these might not be human approximations of how reality behaves. They might be reality itself, expressed in its most fundamental language. Yet even within mathematical realism, we encounter layers of necessity. Some mathematical truths appear more fundamental than others. Arithmetic seems more basic than calculus. Logic appears to underlie all mathematical reasoning. This suggests a hierarchy of mathematical structures, with the most fundamental serving as the foundation for all others. At the apex of this hierarchy lies logic itself. The principles of non-contradiction, identity, and sufficient reason that make coherent thought possible. These logical principles cannot be proven without employing themselves, suggesting they represent the bedrock of all rational discourse. If these principles exist by necessity, then everything that follows logically from them might also exist by necessity. This creates a breathtaking possibility. Our entire universe, with all its complexity and beauty, might be nothing more than the inevitable consequence of basic logical principles working themselves out across space and time. The birth of stars, the evolution of life, the emergence of consciousness, all might be as necessary as the fact that 2 + 2 = 4. However, mathematical realism faces a formidable challenge, the problem of selection. Mathematics contains infinite possible structures, infinite potential universes, infinite ways of organizing matter and energy. If all mathematical structures exist by necessity, why does our particular universe, with its specific physical constants, its particular laws, its unique history, exist rather than countless alternatives? Consider the fine-tuning of physical constants. The strength of gravity, the mass of the electron, the rate of cosmic expansion, all appear precisely calibrated to allow for the formation of stars, planets, and life. In a universe where gravity was slightly stronger, stars would burn out too quickly for life to evolve. If the electromagnetic force were different, atoms could not form stable bonds. These constants appear to occupy an incredibly narrow range compatible with complexity and life. If mathematical necessity determines what exists, then these constants should be as inevitable as mathematical theorems. Yet their apparent fine-tuning suggests either extraordinary coincidence or deliberate selection. This tension points toward deeper questions about the relationship between mathematical possibility and physical actuality. Some theorists propose a radical solution. Perhaps our universe bootstraps itself into existence through mathematical self-consistency. In this view, the universe exists because it is the unique mathematical structure that can consistently describe itself. The laws of physics are not imposed from outside, but emerge as the only self-referential system that can maintain logical coherence. This bootstrap principle finds support in certain interpretations of quantum mechanics, where observation plays a fundamental role in determining reality. If consciousness and mathematics co-evolve within a self-describing system, then the universe might exist precisely because it has developed the capacity to understand itself mathematically. Such a universe would be neither created nor eternal in the traditional sense. Instead, it would be logically necessary, existing because non-existence would be self-contradictory. The question, why does anything exist, would have a surprising answer, because something must exist for the question to be coherent. Yet even if mathematical structures provide the foundation of reality, fundamental questions remain. Why do these particular mathematical principles hold rather than others? Why does logic itself exist? Why is reality mathematical rather than chaotic or ineffable? We might be approaching the boundaries of explanation itself. Perhaps mathematical necessity represents the deepest level of explanation possible, the point beyond which why questions lose meaning. Just as we cannot ask what caused logic without employing logic in our question, we might not be able to explain mathematical existence without assuming mathematical frameworks. This limitation does not diminish the power of mathematical explanation, but rather reveals its scope. If mathematics provides the architecture of existence, then understanding mathematical necessity becomes our deepest form of understanding reality itself. The eternal realm of numbers might not answer every question about existence, but it transforms our conception of what kinds of answers are possible. The mathematical foundations of reality remain one of the most profound mysteries in science and philosophy. Yet this mystery points toward a remarkable conclusion. The universe might not be a strange accident in an otherwise empty void, but rather the inevitable expression of logical necessity itself. In mathematics, we might glimpse the mind of existence itself. The mathematics underlying our universe presents us with an extraordinary puzzle. These equations, these fundamental constants, these precise relationships that govern everything from quantum interactions to galactic formations, they exist with such exactitude that the slightest alteration would render reality impossible. This mathematical foundation raises a profound question. What accounts for the existence of these laws themselves? Consider the gravitational constant. Its value determines whether stars can form, whether planets can maintain stable orbits, whether the delicate balance required for complex chemistry can emerge. Change it by the smallest fraction, and the universe collapses into chaos or expands into sterile emptiness. The same precision appears across every fundamental force, every particle mass, every coupling constant in our physical theories. This observation compels us toward a startling possibility. Perhaps existence itself requires a necessary foundation, something that must exist, that cannot fail to exist, that contains within its very nature the reason for everything else. Gottfried Wilhelm Leibniz confronted this enigma 3 centuries ago with characteristic precision. His formulation remains one of philosophy's most rigorous attempts to answer why anything exists at all. Leibniz argued that every fact demands a sufficient reason. Nothing occurs without adequate cause. Apply this principle to existence itself, and we encounter an unavoidable conclusion. If the universe is contingent, if it could have failed to exist, then its existence demands explanation. But any explanation referring to another contingent entity simply pushes the question backward. A contingent cause requires its own cause, which requires its own cause, generating an infinite regress that explains nothing. Logic demands we terminate this chain with something fundamentally different, a necessary being. This necessary being possesses a unique characteristic. It contains the reason for its existence within its own nature. Unlike contingent entities that depend on external factors, this being exists by logical necessity. Its non-existence would constitute a contradiction. Just as mathematical truths like 2 + 2 = 4 cannot be false, this necessary foundation cannot fail to exist. Leibniz identified this necessary being with God, but the argument's structure transcends religious interpretation. What matters is the logical requirement. If anything contingent exists, something necessary must exist to ground it. What characteristics must such a necessary foundation possess? First, it cannot be composite. Any entity with parts depends on those parts for its existence, making it contingent rather than necessary. The necessary being must be simple, without division or complexity that could introduce dependency. Second, it must be eternal. Temporal beings have beginnings and endings, requiring explanations for why they emerge when they do. Necessity admits no temporal limitations. It exists outside time's constraints entirely. Third, it must be the source of all possibility. Since contingent reality depends on it for existence, this necessary foundation must contain within itself the potential for every actual state of affairs. It serves as the ultimate ground of possibility itself. These characteristics align remarkably with traditional theological concepts, yet they emerge from purely logical analysis. Whether we interpret this necessary foundation as personal deity, abstract principle, or cosmic ground makes no difference to the argument's validity. Contemporary philosophers have raised sophisticated objections to necessary being arguments. Bertrand Russell famously declared the universe just there, and that's all. A brute fact requiring no further explanation. Why assume existence needs ultimate grounding? Perhaps contingency extends infinitely downward with no necessary foundation whatsoever. This response faces serious difficulties. If everything that exists is contingent, then the totality of existence is contingent. But contingent collections of contingent entities remain contingent. They could have failed to exist entirely. We return to our original puzzle. Why does this contingent totality exist rather than nothing? Some philosophers propose that existence itself is necessary. On this view, something must exist, not any particular thing, but existence as such cannot be absent. This position preserves the insight that pure nothingness is impossible, while avoiding commitment to any specific necessary being. Yet this modification raises new questions. If existence as such is necessary, what determines which particular forms of existence become actual? Why this universe rather than some other possible arrangement of existing entities? Modern physics appears to challenge necessary being arguments by explaining cosmic origins through quantum processes. If universes can emerge spontaneously from quantum vacuums, perhaps we need no eternal foundation after all. This objection misunderstands the argument's scope. Quantum field theory presupposes mathematical structures, physical laws, and probabilistic relationships. These frameworks themselves require explanation. Even if quantum processes can generate space-time and matter, they cannot generate the logical and mathematical foundations that make quantum processes possible. The quantum vacuum represents a specific physical state governed by precise equations. Why do these equations exist? Why do they take their particular forms rather than alternatives? Quantum cosmology pushes the explanatory requirement deeper but cannot eliminate it entirely. Furthermore, quantum processes operate according to probabilistic laws, but probability itself presupposes a framework of logical relationships. The mathematics underlying quantum mechanics, complex Hilbert spaces, operator algebras, symmetry groups, exhibits the same precision and necessity that originally motivated the argument. Recent developments in theoretical physics suggest reality's fundamental substrate might be informational rather than material. If the universe consists ultimately of information processing, of computational relationships between abstract entities, then the necessary foundation might be mathematical rather than traditionally theological. This perspective finds support in the unreasonable effectiveness of mathematics in describing physical reality. Eugene Wigner noted that mathematical structures developed for pure theoretical interest consistently prove essential for understanding natural phenomena. Why should abstract mathematics correspond so precisely to physical reality unless they share common foundations? If mathematical objects exist necessarily, if numbers, geometric relationships, and logical structures constitute eternal features of reality, then perhaps physical existence represents the actualization of mathematical possibilities. The necessary being becomes the mathematical realm itself, existing timelessly and grounding all contingent manifestations. This mathematical Platonism faces its own challenges. How do abstract mathematical objects give rise to concrete physical processes? What principle determines which mathematical structures become physically instantiated? Even necessary mathematical existence requires explanation for why these particular structures rather than alternatives. Traditional theistic interpretations of necessary being arguments conclude with a personal God, an agent capable of choice, creativity, and relationship. Contemporary versions often prefer impersonal principles, mathematical structures, logical necessities, or abstract foundations without consciousness or intentionality. This distinction carries profound implications. Personal, necessary beings can account for the apparent fine-tuning of physical constants through intentional design. Impersonal principles must explain this precision through different mechanisms, perhaps anthropic selection effects or mathematical inevitability. Personal interpretations also address the transition from necessary foundation to contingent reality through creative action. An eternal mind can choose to actualize specific possibilities from the infinite range of potential worlds. Impersonal principles require some selection mechanism to determine which possibilities become actual. Yet personal interpretations face the challenge of divine simplicity. If the necessary being is truly simple and unchanging, how can it engage in temporal creative acts? How can an eternal, immutable entity enter into relationships with changing, finite realities? Modern versions of necessary being arguments incorporate insights from contemporary science and philosophy. The Leibnizian cosmological argument emphasizes logical reasoning from contingency to necessary existence. The Thomistic version focuses on causation and the impossibility of infinite causal regress. The modal ontological argument uses possible world semantics to establish necessary existence from the concept of maximal greatness. Each approach faces specific objections, but their convergence suggests something significant about reality's structure. Whether through logical analysis of contingency, causal reasoning, or modal logic, multiple independent arguments point toward some form of necessary foundation underlying contingent existence. The strength of these arguments lies not in any single formulation, but in their collective force. Even if individual versions encounter difficulties, the recurring insight that contingent reality requires necessary grounding appears remarkably robust across different philosophical frameworks. As we stand at the intersection of ancient philosophical wisdom and cutting-edge scientific discovery, the question of necessary existence remains as compelling today as it was for Leibniz 3 centuries ago. The mathematics governing our universe, the precise calibration of natural constants, the very possibility of rational inquiry, all point toward foundations that transcend the contingent realm of everyday experience. Whether we interpret this necessary foundation in theistic, mathematical, or entirely novel terms, its logical requirement seems inescapable. Something must exist necessarily to ground the contingent reality we observe. The mystery lies not in whether such grounding exists, but in understanding its ultimate nature and relationship to the world we inhabit. The universe you observe around you, with its precise physical constants, its delicate balance allowing stars to forge heavy elements, its exact conditions permitting complex chemistry and ultimately life, represents just one possibility among an inconceivably vast array of alternatives. Contemporary cosmological research suggests that our Big Bang may constitute merely a single bubble within an infinite cosmic foam, where countless universes emerge, evolve, and perhaps decay according to their own unique physical laws. Consider the fundamental constants that govern our reality: the strength of gravity, the mass of the electron, the rate of cosmic expansion. Each of these values falls within an extraordinarily narrow range that permits the existence of galaxies, stars, planets, and biological complexity. Alter any of these constants by even minute amounts, and the universe becomes a sterile expanse of elementary particles, or collapses before structure can form, or expands so rapidly that matter never condenses into stars. This apparent fine-tuning has puzzled physicists and philosophers for decades. Why do the laws of physics seem so precisely calibrated for complexity and life? The multiverse hypothesis offers a radical solution. Perhaps they are not calibrated at all. Perhaps every possible combination of physical constants and natural laws exists somewhere within an infinite collection of universes. Modern cosmological theories provide mechanisms for generating such multiplicities. Eternal inflation theory, developed by physicists including Alan Guth and Andrei Linde, describes how quantum fluctuations in the early universe's energy fields could spawn endless regions of space-time, each undergoing its own inflationary expansion. These pocket universes would emerge continuously within an ever-expanding cosmic medium, creating what cosmologists term the multiverse. Within this framework, the specific properties of our universe, including the values of fundamental constants, result from random quantum processes during our particular region's inflationary period. Some pocket universes would possess physical laws radically different from ours. Perhaps gravity operates as a repulsive rather than attractive force, or perhaps the electromagnetic interaction fails to bind electrons to atomic nuclei. The vast majority of these universes would remain sterile, devoid of the complex structures necessary for chemistry, biology, or consciousness. String theory amplifies this possibility exponentially. The mathematical framework describing fundamental particles as vibrating strings rather than point particles suggests an astronomical number of possible vacuum states, perhaps 10 to the power of 500 different configurations of space-time geometry and field strengths. Each configuration would correspond to a universe with distinct physical laws and constants. This string landscape implies that virtually every mathematically consistent set of natural laws finds expression somewhere within the multiverse. This cosmic diversity provides an elegant resolution to the fine-tuning problem through what physicists call the anthropic principle. We observe a universe amenable to complexity and life, not because the cosmos was designed or destined for our existence, but because we could only evolve to ask such questions within a universe possessing the requisite physical properties. Universes lacking these properties exist in abundance, but they contain no observers capable of contemplating their own existence. Think of this principle as a vast cosmic lottery with an infinite number of tickets. While any individual ticket has vanishingly small probability of winning, someone must eventually win if enough tickets are drawn. Similarly, while any specific universe has negligible probability of supporting life, observers will necessarily find themselves within life-supporting universes if sufficiently many universes exist. The anthropic reasoning extends beyond fundamental constants to cosmological properties. Our universe exhibits a remarkably uniform temperature across vast regions of space, yet contains small density fluctuations that eventually amplified into galaxies and galaxy clusters. These seemingly contradictory features require specific initial conditions that appear highly improbable. Within a multiverse framework, however, every possible combination of initial conditions occurs somewhere, and we necessarily observe conditions compatible with our existence. Alternative interpretations of quantum mechanics suggest additional routes to multiplicity. The many worlds interpretation, originally proposed by Hugh Everett III, posits that quantum measurements do not collapse wave functions into single outcomes, but rather split reality into parallel branches corresponding to each possible measurement result. Every quantum event, and quantum events occur continuously throughout the universe, generates new branches of reality. This quantum branching produces an exponentially growing number of parallel universes, each representing different histories of quantum events. In some branches, you chose coffee rather than tea this morning. In others, specific genetic mutations led to different evolutionary pathways, or particular radioactive decays influenced the formation of stars and planets. The totality of these branches encompasses every physically possible sequence of events. Unlike the cosmic multiverse of eternal inflation, quantum parallel worlds share identical physical laws but differ in their historical development. This creates a more constrained form of multiplicity where the same fundamental constants and natural laws generate divergent cosmic stories through the accumulation of quantum uncertainties. Multiverse theories face significant conceptual challenges when attempting to make testable predictions. If infinitely many universes exist with varying properties, how do we calculate the probability of observing any particular phenomenon? This measure problem threatens to render multiverse hypotheses scientifically meaningless by making all observations equally likely. Cosmologists have proposed various solutions involving mathematical prescriptions for comparing infinities, methods for assigning relative weights or measures to different regions of the multiverse. Some approaches focus on the volume of space-time occupied by different types of universes, while others emphasize the number of observers capable of making measurements. These technical debates reveal how multiverse theories push the boundaries of conventional scientific methodology. The measure problem also highlights deeper philosophical questions about the nature of scientific explanation. Even if multiverse theories successfully account for observed fine-tuning, do they truly explain why something exists rather than nothing? Or do they merely push the fundamental mystery to a higher level, leaving us to wonder why the multiverse-generating mechanisms themselves exist? Despite their speculative nature, some multiverse theories generate potentially observable consequences. Eternal inflation predicts that our universe should exhibit nearly flat spatial geometry and specific patterns of temperature fluctuations in the cosmic microwave background radiation. Predictions that match current observations with remarkable precision. However, these same predictions follow from standard inflationary cosmology without invoking multiple universes. More distinctively, some multiverse models predict occasional collisions between expanding bubble universes which could leave detectable imprints in the cosmic microwave background. Researchers have searched for circular patterns or temperature anomalies that might indicate such collisions, though no conclusive evidence has emerged. String theory's landscape of vacuum states might also produce observable signatures through the distribution of fundamental constants across different regions of space-time. If our observable universe spans regions with slightly varying physical laws, we might detect gradual changes in particle masses or coupling strengths across cosmic distances. The multiverse hypothesis reveals a profound recursion in our quest to understand existence. We began by asking why something exists rather than nothing, and discovered that modern physics provides mechanisms for spontaneous creation from apparent nothingness. The multiverse extends this logic. Perhaps existence is not only possible, but inevitable when infinite possibilities are explored. Yet this multiplication of realities does not eliminate the fundamental mystery. It transforms it. Instead of asking why our particular universe exists, we now ask why the multiverse-generating mechanisms exist. Why do quantum fields undergo eternal inflation? Why does string theory describe fundamental reality? Why do the mathematical structures underlying these theories possess their specific properties? The multiverse may represent either a deeper understanding of existence or a retreat into infinite regress. By making everything possible, it may explain nothing at all. Alternatively, it may reveal that the question, why something rather than nothing, rests on false assumptions about the nature of existence itself. In pushing beyond the boundaries of our observable cosmos, Multiverse theories force us to confront the limits of scientific explanation and the relationship between mathematical possibility and physical reality. They suggest that the universe, or multiverse, may be far stranger and more abundant than we ever imagined, transforming our cosmic perspective from one of precious rarity to overwhelming multiplicity. The question remains whether this transformation brings us closer to understanding why anything exists or merely reveals the depths of our cosmic ignorance. The multiverse stands as both the most ambitious attempt to explain our universe's apparent fine-tuning and the most challenging puzzle for those seeking ultimate explanations of existence itself. The universe has produced something extraordinary, beings capable of questioning their own existence. You are not merely a collection of atoms observing other atoms. You represent the universe's attempt to understand itself, a phenomenon so improbable that its very occurrence demands examination. Consider the statistical impossibility of your awareness. From the primordial quantum fluctuations that birthed space-time, through billions of years of stellar nucleosynthesis, planetary formation, and biological evolution, the universe has generated structures capable of contemplating their own origins. Your brain contains approximately 86 billion neurons, each forming thousands of synaptic connections, creating a network more complex than the visible universe's estimated number of stars. This complexity emerged without design, without blueprint, through the blind application of physical laws. Yet these same laws produced entities, conscious observers, who can formulate questions that transcend immediate survival needs. Why would natural selection favor brains capable of pondering metaphysical mysteries that provide no evolutionary advantage? The neuroscientist Christoph Koch argues that consciousness represents an emergent property of information integration. When neural networks reach sufficient complexity and interconnectedness, subjective experience arises. But emergence explains mechanism, not purpose. The deeper question remains, why should the universe generate observers at all? Quantum mechanics reveals something unsettling about observation itself. The act of measurement appears to collapse wave functions, transforming probability clouds into definite outcomes. This suggests consciousness plays a fundamental role in determining physical reality, not merely observing it, but partially creating it through the process of observation. The anthropic principle extends this insight to cosmic scales. We observe a universe finely tuned for complexity because universes lacking such precision would contain no observers to notice their absence. The strength of nuclear forces, the mass of fundamental particles, the rate of cosmic expansion all fall within narrow ranges, permitting the emergence of stars, planets, chemistry, and ultimately life. But this reasoning contains a circularity that reveals something profound about existence itself. We exist in a universe that permits our existence because we are here to observe that it permits our existence. This logical loop suggests that consciousness and cosmos are more intimately connected than classical physics assumed. Your ability to question existence creates a paradox philosophers call self-reference. When you ask, why is there something rather than nothing, you presuppose your own existence as a questioner. The question cannot be posed without something already existing to pose it. This paradox illuminates a deeper structure in reality. Every attempt to examine existence from outside existence fails because the examiner remains part of what is examined. You cannot step outside the universe to observe it objectively because you are woven into its fabric at the most fundamental level. The mathematician Kurt Gödel demonstrated that sufficiently complex formal systems cannot prove their own consistency from within themselves. Similarly, perhaps the universe cannot explain its own existence using only the tools and categories generated by that existence. The question, why something rather than nothing, may represent consciousness encountering the absolute limits of its own explanatory power. Your mind possesses a remarkable ability. It can discover mathematical truths that accurately describe physical reality. Eugene Wigner called this the unreasonable effectiveness of mathematics in the natural sciences. Why should abstract mental constructs correspond so precisely to the behavior of matter and energy? The Pythagorean theorem, derived through pure thought, governs the geometry of space-time. Complex numbers, initially dismissed as mathematical curiosities, prove essential for quantum mechanics. Prime numbers, studied for their intrinsic beauty, underpin cryptographic systems that secure global communications. This correspondence suggests either a deep unity between mind and cosmos, or that mathematics represents something more fundamental than both physical reality and mental activity. Perhaps mathematical structures constitute the deepest level of existence, with both consciousness and matter emerging as manifestations of underlying logical relationships. The universe exhibits a recursive property. It generates entities capable of understanding the very processes that generated them. Through scientific inquiry, you have decoded the nuclear fusion processes that forged the atoms in your body, mapped the evolutionary pathways that shaped your neural architecture, and reconstructed the cosmic history that culminated in your existence. This recursion suggests that existence possesses an inherent drive toward self-comprehension. The universe evolved beings capable of discovering its own deep structure, almost as if physical reality contains a hidden imperative to be known. Stars manufacture the chemical elements necessary for complex chemistry, planets provide stable environments for biological evolution, and organisms develop nervous systems sophisticated enough to perceive mathematical order in natural phenomena. The physicist John Wheeler proposed that this feedback loop between observers and observed might be fundamental. In his it-from-bit hypothesis, he suggested that information, not matter or energy, represents reality's foundation. Every measurement, every conscious observation, every act of understanding contributes to the ongoing creation of the universe's self-definition. Your quest to understand why anything exists encounters philosophical boundaries that may be absolute. The British philosopher Bertrand Russell argued that the universe represents a brute fact, requiring no further explanation. The universe is just there, and that is all. This position, known as explanatory nihilism, suggests that the demand for ultimate reasons reflects a cognitive bias rather than a legitimate philosophical requirement. Yet this conclusion feels intellectually unsatisfying precisely because your mind possesses the capacity to seek deeper explanations. The very dissatisfaction you experience when told there is no why indicates that consciousness embodies a principle of intelligibility that transcends immediate practical concerns. Perhaps the universe's deepest mystery is not why it exists, but why it generates beings compelled to ask that question. Your curiosity about ultimate origins may represent something more significant than mere evolved psychology. It might reflect consciousness participating in reality's drive towards self-understanding. Modern physics suggests that observers and observed form an integrated whole, rather than separate categories. Quantum entanglement reveals that particles maintain instantaneous correlations across cosmic distances, implying that locality, the idea that objects are only directly influenced by their immediate surroundings, fails at the deepest level of reality. Your consciousness does not simply observe a pre-existing universe, it participates in the ongoing process of cosmic becoming. Every measurement collapses quantum superpositions, every calculation reveals hidden mathematical relationships, every moment of wonder acknowledges the improbable fact of existence itself. This participatory perspective suggests that the question, Why is there something rather than nothing? Cannot be answered from a detached, objective standpoint, because no such standpoint exists. You are not asking about existence from outside existence. You are existence asking about itself, the universe using your neural networks to examine its own foundations. The physicist Freeman Dyson observed that the universe knew we were coming. This poetic statement captures a profound insight. The cosmos exhibits precisely the characteristics necessary to generate entities capable of comprehending cosmic evolution. Whether this represents coincidence, necessity, or something more mysterious remains one of existence's deepest puzzles. Through your consciousness, the universe achieves something unprecedented in its 13.8 billion-year history, the capacity for self-reflection, wonder, and the recognition of its own astonishing improbability. You are not merely in the universe, you are the universe becoming conscious of itself, matter achieving the ability to contemplate its own existence, and the cosmos asking the question that defines the ultimate mystery. Why is there anything at all?